Today we are interested to find out the low pass equivalent of a band pass signal. So now let me show you the band pass signal. So if we see our band pass signal, it looks like this, right? It's something like this, some arbitrary shape. Because say our signal is real, so it will have this component at minus f naught as well. So this is the spectrum of a real signal. So if you have a real x of t, the band pass signal, looks like this. You have a signal in this band, right? We call it a band pass signal, and keep in mind your frequency f naught is much greater than 0. So your signal is in this band. Now we define the spectrum as the positive frequencies of the signal, positive frequencies of x of f. So positive frequencies of x of f. So we call it, this is the bandwidth of this signal. Let's define the positive and negative spectrum of x of f. So we would say that x positive of f is this signal, right? And we define this one as x negative of x. We say that this is the positive and the negative spectrum, the positive spectrum of x of f and the negative spectrum of x of f. And of course your x of f, you can always write that your x of f is x positive of f plus x negative of f, right? So this is our x of f. Now if you because this is a real signal, so for real signal, the Fourier transform has Hermitian symmetry. And what do we mean by Hermitian symmetry? We say that the in simple words, we say that the magnitude response of x of f, let me clarify. When we say Hermitian symmetry, we say that x of minus f is same as x conjugate of f. By Hermitian symmetry, we say that x of minus f is same as x conjugate of f. And when we say x of minus f is same as x conjugate of f, for the real signal x of t, we simply mean that the magnitude response of x of minus f is same as the magnitude response of x of f, right? This x of minus f is the mirror image of x of f, and its phase response has this property. It is negative of x of f, which means that the magnitude response is actually an even function. It is an even function, while the phase response is actually an odd function. So the phase is odd function, right? Is the by the definition of the even function and odd function, we can say that you are familiar with the definition of the even and odd function. And a simple example is your cosine wave, right? Your cosine wave like this. So it is an even function. If this is your if suppose this is your x of t, right? So x of minus t would be mirror image, and you will get the same. You will get the same image for x of minus t, because if you see the mirror image around 0, you will get the same as x of t. So if you want to find out the magnitude response, you will get the same magnitude. And when we say the even the simple example in the time domain, the odd function is sinusoid. Right? Now if you take the mirror image of this sinusoid, if you observe it, if you take the mirror image here, suppose this is your this is the example of odd function. This is an odd function. If you take the mirror image, it would look like this. See your mirror image. Your mirror image would look like this. This is like a positive. So it would be. This is the mirror image, something like that. Right? So this is your mirror image, and the mirror image we can see it's x of minus t. The one in the blue is x of minus t, and the one in the black is x of t. We can clearly see that this is the negative x of minus t. X of minus t is actually equal to minus x of t. Right? So for the even function, x of minus t would be equal to minus x of, for odd function, for odd function x of minus t would be equal to minus x of t. Because if you now take its negative, this is x of, this blue is x of minus t. If you take you have x of t as well. So if you take the negative of x of t, you would get this x of minus this blue. The negative is this one. So these are the simple example of your odd and even function. Or you can just simply you can also say that, okay, even function, in even function, if you select certain point, certain instant here, for example t1, so whatever is the value of the function at t1, you will have the same value of the function at minus t1, same value, it will be the same value, t1 and minus t1. But here, if you select an instant t1, you have a value this one, but for the same instant, this is t1, the same instant minus t1, you will have the same value, which is negative. Magnitude will be same, but it will be negative. So this property, so of minus t is minus x of t, is can be observed in the odd and the even function. Right? So this is for the odd and even function. So we define the positive spectrum and the negative spectrum of our signals, right? The positive spectrum and the negative spectrum of x of f. Now if we want to write it mathematically, how would we write our positive spectrum? Our positive spectrum is actually the same as x of f for f greater than 0, and it is half of x, the function value at 0, when your function is 0, and it is for f less than 0. This is the definition of our positive, x positive of f, right? And x negative, the negative spectrum, we would define as this one. It is the same as x of f for f less than 0. For negative, it would be half at origin and 0 when the frequencies are greater. So this is the definition for the negative spectrum. And you can, if you have a baseband signal, whether you have a baseband signal or a passband signal, you can define, you can use this definition. So this would be our x positive of f, and this would be our x negative of f. This is for a baseband signal, when we have a baseband signal or a low pass signal. We say a low pass signal. At the origin we take half, so half is associated with the positive spectrum and half is associated with the negative spectrum, this magnitude. Now if you consider it for a band pass signal, so you have a band pass signal x of f, band pass signal, and it is in this particular band, so this is frequency f naught. So this would be x positive of f, right? And this part, it's a real signal, so the same signal is here as well. So this would be x negative of f. So you have x positive of f and x negative of f, and of course your x of f is the summation x positive of f plus x negative of f. So we can write our positive spectrum and negative spectrum in this way. We can also write the positive spectrum x positive of f to be x of f multiplied by the unit step function. Unit step function is unity for f greater than 0, as so we have, by definition, we know that the unit step function, this unit step function, the definition, we know that our unit step function, we define our unit step function as 1 when f is greater than 0, and half when f equals 0, and 0 for f less than 0. This is the definition of our unit step function. We are using this definition of unit step function, right? So similarly you can also define your x negative of f, the negative spectrum. You can rewrite it as, in terms of x of f, you can rewrite that this is x of f u of minus f, right? So we can write our negative spectrum and positive spectrum in terms of x of f. It's the same x of f, u of minus f. So u of minus f only exists for negative frequencies, right? So it's unity for f less than 0. You can say the mirror image of u of f. So when the signal x of t is real, x of f is Hermitian. When we say x of t is real, right? X of t is real, and we say our x of t is real. So it means that its Fourier transform possess Hermitian property. And what do we mean by Hermitian property? We mean by Hermitian property that the x of minus f is x conjugate of f. This is when you have Hermitian property, you have this is known as the Hermitian property. If you take the conjugate, x conjugate frequency response, we have some certain expression for the x of f, and if you take the conjugate there in that expression, it would be same as x of minus f. And when we say it is same, we can rewrite it we can rewrite it in this form. See, we say that the magnitude the magnitude of x of minus f, it is same as the magnitude of x conjugate of f, right? We say that the magnitude is same. So if the magnitude is same, we also saw in the previous diagram that x of minus f, the negative spectrum, can be obtained from the positive spectrum, right? The negative spectrum can be obtained from the positive spectrum. How? Let's see this example. Suppose you have a signal, this one, right, a baseband signal. Similarly, you can do it for a passband signal. You have this signal. So this is the positive spectrum, x positive of f, and this one is the negative spectrum. So you can obtain the negative spectrum x minus of f by mirror image of x positive of f, right? Mirror image of x positive of f. So this, the mirror image of x positive, can be drawn here. We say the mirror image, so this part mirror image, you will get this thing. Now what happened, it has the if you observe the phase response of the real signal, it looks like this. So for the negative spectrum, the phase response will be like this. It's a negative, while here for positive it is positive. So you need to have this conjugate, you need to have here conjugate to perfectly show that this is actually x of the negative spectrum can be obtained from the positive spectrum by having its mirror image and conjugate. When we say conjugate, we turn its phase to the we say it's negative. Instead of this one, now the phase would be this one, which is same as, this is the amplitude, this is the, and this one is drawn for the phase. So this conjugate make the phase negative, make the phase response negative, which is the same as for x minus of f, right? So you have the negative spectrum can be obtained from the positive spectrum if it has the Hermitian property and if it is a real signal. So we always we will talk about the real signal. So discussing the real signal, now let me discuss this real signal. We are interested in a real bandpass signal, real bandpass signal, this magnitude and this positive spectrum. Now we would like to derive an expression. We would like to derive an expression for this x plus of t. Right? We would like to derive an expression for x plus of t. Now if you observe this x positive of f, we can rewrite x positive of f, or the positive spectrum, as x of f u of f, unit step function, right? So what will happen if you, in your x of f has both the, because it's a real signal, so your x of f has both these positive and negative spectrum. When you multiply it with the unit step function, this part is suppressed, so you are only left with the positive spectrum, x positive of f, right? So we can write our x of f in this form, and we can now what we would like to do from here, we would like to derive the x of t, x positive of t, from this expression. So how we can get x positive of t, right? Because this is in frequency domain, right? So if we take the Fourier inverse, so we take the Fourier inverse of this side, right? X positive of f, and we say the Fourier inverse of the right hand side, which is x of f u of f. If we take the Fourier inverse of x positive of f would be x of t, x positive of t. And the Fourier inverse here, you can see this is the x of f multiplied with the unit step function. It's a product. So when you have a product in the time domain, the corresponding, if you see the properties of the Fourier transform, a product in frequency domain means the convolution of those signals in time domain, right? The convolution of those signals. So the convolution of x of t, x of f has a time domain pair x of t, and we will see the time domain signal for the units u of f. So their time domain pairs would be convolved, right? The product in the frequency domain is same as equivalent to the convolution in the time domain. So from here we get that left hand side will give us x positive of t, which is equal to the convolution of x of t, which is equal to the convolution of x of t with the time domain signal here u of f. And if you observe your Fourier tables, the u of f has, this is the convolution sign, right? Let me draw the convolution sign. So the convolution of the signal corresponding to u of f, and u of f is actually half delta t. This is taken from the Fourier table. So if you observe your Fourier table, it is j 1 over let me erase this one, 1 over 2 pi t. So this is the Fourier pair which is taken from the signal. Like this signal in time domain has response u of f, Fourier pair u of f, frequency response is u of f. So it's the convolution. Here it is a product, here it is convolution. This is the convolution. Now moving ahead, if we see that x of t convolved with delta of t. So first when you convolve x of t with half delta t, you would get a half x of t as a result of this convolution. And if you convolve x of t with 1 over 2 pi t, right, we write this part x of t convolved with 1 over 2 pi t as j 1 over 2 pi t as j x hat of t. So we write the other part x of t convolved with j 1 over 2 pi t as this one. Now this is our x positive of t. This term you will see it is actually the convolution of x of t with j 1 over 2 pi t. Now to find out, this is actually known as the Hilbert transform of x of t, right? So x hat of t is known as the Hilbert transform of x of t. Hilbert transform of x of t, right? So this is the Hilbert transform of x of t, and we said that we say that our x hat of t is actually convolution of x of t with j. The convolution of j is there, so you don't need this j. It's the convolution of x of t and 1 over actually pi t, this thing. Now let's try to find out x hat of t, because this is the key. Now the other part is just x of t, right? So what actually this part is, let me write it in the frequency domain, because we, instead of convolution, we will deal with the product, so this convolution would change into the product. So if I say that I have the Fourier of this, I take the Fourier transform now. The Fourier transform of x hat of t, let me represent it by x hat of f. It would be, this is the convolution time domain, so the frequency domain, you have to convolve, you have to find out the product of these their pairs. So x of t in frequency domain is x of f. Now it has to be multiplied with the frequency domain pair of this thing. Now if you observe the pair from the Fourier table, if you observe the Fourier table, you have a Fourier pair for 1 over t. So the Fourier pair for 1 over t is actually, let me write it over here. If you observe your tables, the Fourier pair for 1 over t is minus j pi and signum function of f. Sg is the signum function, right? Signum function, which is 1 for positive f and minus 1 for negative f, negative frequencies, right? The signum function. So if you want to draw the signum function, you can draw it here in f frequency domain. It is 1 for, it is plus 1 for all f. It is minus 1 when f is less than 0. So actually this is either plus 1 or minus 1, this part. Well, we have 1 over pi also. So if you divide this side by pi, you will divide this side, this whole by pi, right? So if you divide this by pi, this pi cancels, and you are left with the frequency. You are left with the response 1 over pi t as a Fourier pair minus j signum of f. So substitute this now, the product, right? So we can substitute this value to find out that product. Now what do we have? We have our, let me write it, or instead of writing below, let me write it there. So you have x of f, you have x of f, right? Where x of f is already here, and the Fourier pair here, we just say that this is j, this is minus j signum of f, minus j signum of f. So this is the Fourier transform, of x of f, right? So if we have this Fourier transform, now let me rewrite it somewhere. I would like to rewrite it below just to solve it further. So we just saw that our x hat of f, our x hat of f is actually equal to, x hat of f is actually equal to minus j signum function of f multiplied by x of f. right? Now it is derived from x of f, if you see. So we have the x hat of f is actually derived from x of f, and what happens with this x of f? The signum function. Try to understand this expression. The signum function is positive 1 for now x of f. If you observe your x of f, it has a positive spectrum and a negative spectrum. So for positive spectrum, this part is positive, so you are left with only minus j. So the positive spectrum is multiplied with minus j, and if you observe this minus j, what is actually minus j? Just a complex number, and it has the magnitude equal to 1, and the phase of minus j is minus pi by 2, 90 degrees, minus pi by 2. So what actually happens when you multiply x of f with minus j, or the positive spectrum with minus j, it changes the phase of positive spectrum, all the positive frequencies which contained in the positive spectrum, by minus pi by 2. The phase is changed by minus pi by 2. And what will happen to the negative frequencies? Because x of f also has a negative frequency. For negative frequencies, this is minus 1. Right? So minus and minus j, minus 1 is plus j. So for negative spectrum, actually plus j. Now we have plus j for when signum function is minus 1, which is minus 1 for the negative when f is less than 0. So the frequency content of x of f, which is at the negative side, is multiplied by this plus j, and multiplying it with plus j means changing its phase by pi by 2. Changing its phase by pi by 2. So actually this term change the phase of all the positive frequencies of x of f by minus pi by 2, and the negative frequencies of x of f, the negative spectrum of x of f, all the negative frequencies by plus pi by 2. So actually it is a phase shifter. This is a phase shifter. So the Hilbert transform is nothing but a phase shifter of pi by 2, but it acts differently on the positive frequency content and the negative frequency content of the signal. So basically it is a phase shifter. Now we said that it's basically a phase shifter. So we can write, let me rewrite the x hat of f. This is minus j signum of f, x of f, right? Now I hope you understand this signum function, the minus j signum function with x of f. So it is actually derived from x of f, and this is the Hilbert transform. Now we are interested in finding out the low pass equivalent of a bandpass signal, or we say low pass equivalent, or the complex envelope. And we said that our low pass equivalent, when we say low pass equivalent, we are only interested in the positive spectrum, right? And we said that our positive spectrum is nothing but x of f u of minus f, right? This is our positive spectrum. right? So how do we define the low pass equivalent now? How do we define the low pass equivalent? We say that the low pass equivalent of this should be a signal whose spectrum, it's a signal whose spectrum should look like just this positive, this one. Spectrum should look like this here. Let me draw it properly. Should be something like this. So it is actually from here. We want this because we said that all the information is contained in the positive spectrum. But instead of processing this positive spectrum at high frequency, which is f0 is much higher in gigahertz range, it is much higher. So instead of processing it here, we would like to find out its equivalent xl of f. You would like to find out the equivalent circuit, the equivalent signal whose frequency contents look like this, which is same as the content of the x positive of f, but it is located near 0, right? It is located near 0. And how you can do it? You can just, you need this is known as the spectrum of a low pass, the low pass signal, or the spectrum of a low pass signal, low pass equivalent. So we are interested in this spectrum now. So we say that we are interested in a signal whose spectrum looks like x positive of f advanced by f0, right? You want to shift it here. So if you advance it by f0, you would get this waveform. And just to keep the energy same, you can multiply it with 2. Right? Half the energy is in positive spectrum, half is in the negative spectrum. So if you multiply it with 2, the energy of this signal, the energy would be preserved, right? So the energy can be preserved. So the spectrum, we say that our low pass equivalent signal xl of t should have this spectrum, right? It should have this spectrum, which contains all the information of the signal. Now with this spectrum, if it has this spectrum, we would be interested in finding out this low pass equivalent signal, our low pass equivalent signal, which is just the Fourier inverse of xl of f, right? It's in frequency domain. So if we take the inverse Fourier, we would get the time domain signal. Now xl of f, if you observe xl of f, we said that it is 2 times this one, positive frequency shifted here. But we already mentioned that our positive frequency is frequency x of f. If you recall, let me rewrite it. Our positive frequency x of f, this we mentioned this earlier, that positive frequency x of f is x positive spectrum. Positive spectrum is x of f u of f, right? So if you shift it, it means x positive f plus f naught would be equal to x of f plus f naught u of f plus f naught, right? So we can write it in terms of a unit step function, and if you have 2 over here, you can write 2 over here. right? So we have this, we just derive this. I did it for this above equation. Just I would like to write I would like to replace this equation XL of f by this one, right? So let me rewrite it, because we have to take the inverse Fourier now. We have to take the inverse Fourier. So we can say, okay, our XL of t, low pass equivalent, our low pass equivalent signal is the inverse Fourier, of this XL of f, right? This is what we said earlier. It's the inverse Fourier of XL of f, right? And this can be written. This can be written in the form of x positive of t, right? X positive of t, we derive some expression for x positive of t or not? Let me go back. Let's see what we derive for x positive of t. Now we have x positive of f, but we did not derive expression for x positive of t, right? X hat, this one, yeah, we derive it already. So we have this x positive of t, okay? We have x positive of t. This one is x positive of t, right? X positive of t. And x positive of t, we said that this is x of t, x of t and j is Hilbert transform, Hilbert transform, x of t plus the Hilbert transform of x of t. So let me go back to that point and we will continue from there. Now writing our expression, we can rewrite our expression for we can say that this is the Fourier inverse of XL of f. Now it's this function, right? L of f is actually 2 times x positive of the advanced version of x positive of f. So now here we apply the property of the modulation property. X x of x positive of t. Let me write it separately and then I'll explain. X positive of t when multiplied with the complex exponential, right? If we multiply it with the complex exponential minus j 2 pi f naught t, it would have the x positive of f advanced by f naught. It would have this spectrum. This is the we are applying the modulation property, right? The modulation property. So if we substitute just for this one, we have to take the Fourier inverse of this one. So if we take the Fourier inverse of this x sub L of f, we would get this thing. 2 is there, so we can write our 2 here, right? We can write our 2 here. If you have 2 here. So rewrite it, and your signal would look like this. Your XL of t would look like this: x positive of t e raised to the power minus j 2 pi f naught of t, right? So this is from the modulation property. from Fourier tables. You should observe the Fourier tables. Any signal multiplied by e raised to the power of minus j 2 pi f naught t, the spectrum would be x of f, x of f plus f naught. So x positive of t is multiplied, so x positive of f plus f naught would be the spectrum. Now we already have this x positive of f. We have already derived x positive of f, and we said that our x positive of f is actually our x of t plus the Hilbert transform. Imaginary part is the Hilbert transform, and here we have the same 2 pi f naught t. We just substitute x positive of t from the above equation. We just saw this equation. Now if we open it, this is cos of 2 pi f naught t minus j sine of 2 pi f naught t, right? So if we open it, we can rewrite it this way, that we have x of t, actually x of t, just let me rewrite this identity. So we have actually we have 2 times x of t e raised to the power minus j 2 pi f naught t plus 2 times j x hat of t and multiplied with that complex exponential, whatever it is, right? So we just rewrite that equation. Now if we solve it further, you can just open it. E raised to the power j theta is cos of theta plus j sine of theta, right? So we can say this is x of t cos of 2 pi f naught t minus x of minus j x of t sine of 2 pi f naught t 2 pi f naught t right. Now the same multiplication would take place in the other line as well, plus 2j let me select a proper marker, 2j, and we have x hat of t e raised to the power is actually what? Cos of 2 pi f naught t plus j sine, this should be minus j, here we should have minus j sine of 2 pi f naught t, right? So we have to open it now. Open it now. This can be rewritten. We can rewrite it in the form of cos and sine. So the real part can be separated. So we have the real part is here, and we have the real part from this would be here, right? Multiplication of this with 2j with this one would give us the real part. So if we separate the real part, we can write the real part as x of t cos of 2 pi f naught t cos of 2 pi f naught t cos of 2 pi f naught t. It should be minus j square, so you would get a plus get plus x hat of t, x hat of t sine of 2 pi f naught t, right? Sine of 2 pi f naught t. And the next part we can, for the next part we can say that okay, we can have x of t, the imaginary part can be separated. So for the imaginary part we have the imaginary part from, let me point it out here, and this is the imaginary part. So we have j x hat of t cos of 2 pi f naught t minus x of t sine of 2 pi f naught t. So this is actually the imaginary part. This is the imaginary part. So we have a real part, and we have a imaginary part. Now from we can see that the x of t, if you observe this real part, just this one, which is the real part of xl of t, right? It's the real part of xl of t e raised to the power j 2 pi f naught t, it's the real part. So the real part of this low pass equivalent signal, this is xl of t, it's a real part. It can be observed that the real part is actually equal to x of t, right? The real part is actually equal to x of t, and where we said that it's just from our above equation. This is actually our the real part of x of t is, if you see here, let me we can write the real part here, this one. If you see this one, this is the real part of our x of t. So the real part from here, let me bring it to the center of the screen. So we are just taking the real part here. So we take the real part, and the real part of this xl of t equals x of t. If you see above in these equations, we have derived that our x of t, just we had an equation for our x of t. See, this is our bandpass signal x of f, right? Which is a real signal. X of f. So our bandpass signal is a real signal. So easy. You can see here. Let's see, it's our x of t. This one. This is our x of f. So the real part of the xl of t gives us this x of t. See, we have both these function.